Alright, in this last video, we're going to look at problem 10, which is asking us to use geometry to compute the following integrals. Okay, so for part A, we're integrating the function x times y squared over the region D, where D is the unit disk centered at the origin. Okay, so I have my double integral here and our region of integration here, D. And so now I could attempt to actually set this up as an iterated integral, but again, the instructions here are explicitly saying do this just using some geometry. Okay, and so one thing to observe in a problem like this is that our domain here is highly symmetric. Okay, and furthermore, looking at this function, okay, one thing I notice here is that if I think about treating y as a constant for a moment, x there, that's an odd function. So what exactly am I saying there? So let's say I choose a point over here in, say, quadrant 1, and I'll label its coordinates x, y. And then let's say I choose the mirror image point over here, so mirroring about the y-axis, and I look at this point with coordinates negative x, y. Okay, and if I ask you what would be the function value at these 2 points and how would they compare? Well, f of xy is just xy squared, and f of negative xy would equal, well, negative xy squared. So in fact, the function value at a point here in either quadrant 1 or 2, okay, will have a function output that's equal but opposite the output over here in this point that would be the mirror image of our original point about the y-axis. So what is that saying then about the surface defined by f? Well, what it's saying is that we're going to get some behavior here in quadrants 1 and 4, and then we're going to, so let's say, we're positive in both quadrants 1 and 4, which actually would be the case, right? Because x would be positive and this square term for y is always non-negative. So we're going to be positive over here. So that means over here we're going to be negative, but by the symmetry, it's even stronger than that, right? Any volume that would be captured in below our surface and above, say, quadrants 1 and 4, it's going to get canceled out by the corresponding equal but opposite volumes we would get from quadrants 2 and 3. And to add to this, let's bring up this picture here of the surface. You can see that here. So looking down on the XY axis gives us this view. It's really this view that you really want to pay attention to, right? So any volume I'm going to pick up above quadrants 1 and 4, right, that's going to get canceled out by the equal but opposite symmetric volumes, which are counted as negative down here. So when all is said and done, here's what we can say. This condition right here, we'll say, implies that f is an odd function with respect to the y-axis. Okay, that's the line in which the symmetry is being exhibited. And so since our domain of integration D is symmetric about the y-axis, then that means that our integral will simply be 0. And that is really all there is to it. Now this would actually be a pretty difficult calculation if we tried to do this with the iterated integral. Okay, so this obviously is a lot simpler. And yeah, that's going to do it, right? Nice geometric interpretation. All right, let's move on to B. This says, compute this iterated integral, okay, using geometry. Okay, so first, I'm going to go ahead and sketch the region of integration. So notice that these bounds for y are from minus the square root of 16 minus x squared up to the square root of 16 minus x squared. Well, these are describing the top and the bottom halves of circle centered at the origin of radius 4. Okay, so I'm really looking at this circle of radius 4. And now if I fix in x, y is varying from the bottom half, which is my minus the root, to the top half, which is the positive root. So I'm going to get this vertical strip here. And then we're going to stack these vertical strips as we let x vary from minus 4 to 4. Okay, so putting that all together, our domain of integration is in fact this disk here centered at the origin of radius 4. Okay, so now what's our integrand? What is this thing right here? The root 16 minus x squared minus y squared tell us? Oh, well, we've seen this kind of thing now quite a bit. This is just the hemisphere. It's the top half of the hemisphere of radius 4 centered at the origin. So now what am I really looking at? I'm looking at, for our surface, a hemisphere of radius 4. And that boundary down here in the xy plane is nothing other than that circle of radius 4. And our region of integration is, well, the base of our hemisphere. Oh, so really, all this integral is doing is computing the volume of this hemisphere of radius 4. Of radius 4. And so how do you compute the volume of a sphere? Well, it's 4/3 pi r cubed, so a hemisphere would be 2/3 pi r cubed. And that's, what, this would be 64 times 2 would be 128 pi over 3. Okay, so there we go, right? Nice geometric solution. This again would be pretty difficult, pretty messy to actually compute as an iterated integral. Okay, great. And now moving on to the last one. This is C. It says to compute this iterated integral of the function 5 plus x, and we're letting x vary from minus a to a, and y varying from 0 to a, where a is just some positive number. Okay, so again, I'll go ahead and draw our region of integration. And so x is going from minus a to a, and y goes from 0 to a. So we're looking at a rectangle here. It looks like this. So we're going to integrate over that region right there. And so I'll go ahead and call this region R. And what I'm going to do now is I'm going to say this is equal to the double integral over our region R, and we're integrating 5 plus x dA. And now I'm going to split this up. This is going to be the double integral of just 5 dA plus the double integral of x dA. Okay, and so now let's use a few things that we've seen. This right here is what? Well, if you go back to question 3 on the worksheet, this is going to be 5 times the area of our rectangle R. Okay, so, and that's not a hard area to find, right? It's just a rectangular area. And then we're going to add to this integral of just x over our rectangle R. And wait a minute, our domain here, this R, is symmetric about the y-axis. And again, our integrand, since it's just x, is going to be odd with respect to the y-axis, right? So if I look at, say, a point xy, and then its point, which is just mirrored over the y-axis, this would be at negative x, y, then f of xy, if that's just x, then f at negative xy is negative x. And so again, right, we have that f is odd with respect to the y-axis. Okay, and so what does that say? It says, by that same kind of argument we used in part A, that this thing is just going to be 0, okay, by symmetry. So then to finish that all off, what's the area of our rectangle? Well, this is 2a, and this is a. So the area there would be 2a squared times 5. This would be 10a squared. And that's going to do it. All right, great.